So we have very little time, so I'll try to make this quick. So just going to start by pointing out that it's very, very common that and important that we sort of deal with games between teams. Mostly we pay attention to this in sports, which is a very clean example of what I have to talk about. As Christos kindly pointed out, there's decades and decades of literature, beginning with Coase, I guess, in the economics literature on the inefficiencies of firms and how the difficulty of coordination between individuals is actually kind of a limiting factor on the size of an effective firm. So that's more by way of motivation. That's not going to tie in very closely to the model that I'm actually going to tell you about. And what does tie in actually well to the model and that I'll talk about is in the process of sexual selection. You can think of a whole species as a team in which the players are the genes and their choices of actions are the alleles, and that is actually a model of, and then when you have two teams, two species in competition, predator prey or something, that fits actually very nicely this kind of model that I'm going to talk about. We move to the formal model. You have a two-team game is a multiplayer game. The players split into two disjoint sets A and B, and with the following properties of the payoffs, that for any two players in Team A and any actions by all the players, the payoff to A is equal to the payoff for A prime. And then that's what makes it, and the same thing happens in Team B. So Team B also gets, like we all win the basketball game or we all lose it and go home. And then the second property we're going to assume now is that the game that the two teams are playing, just as in the sports example, and as is arguably the case in many interactions in the evolutionary example, is a zero-sum game. So the payoff to Team A is minus the payoff to Team B. So that's the framework we're interested in here. Now to kind of get toward what we need in order to kind of make quantitative statements, we're going to suppose that each team has K players, and the number of choices available, the action space for each player there is of size M. So the payoff matrix, if you will, is really a tensor of sort of order 2K, right? So, but it's, you can think of it as a matrix and you expand out the actions of all the players, but it's properly perhaps thought of as a tensor. And the T, if capital I is a vector of actions by Team 1 or Team A, and capital J is a vector of actions by Team J, then this entry, Tij of the tensor, is the payoff to Team B. In the case K equals 1, so there's only one player per team, we're back to von Neumann, we're back to two-player zero-sum games, and this is not interesting to think about. We're going to K greater than 1. The notation I'll use throughout the talk, yes, I have a pointer here. The notation will use throughout the talk is that when I use a lowercase letter p, that represents a product strategy. So it's a multiplayer game. So it's like you'd have in a Nash equilibrium, but everything has to be a product strategy over all the players. So lowercase, whenever I write lowercase p, that means a product strategy for the players of Team A. A lowercase q is a product strategy for the players of Team B. Capital P and capital Q represent non-product strategies, represents what would happen if the teams internally if they could share coins, okay, within the team, which just makes them actually kind of a virtual player. Okay, so the payoff is just some kind of inner product across this matrix or tensor, but we're interested in what happens in terms of a duality gap, which you may have noticed in the title of the talk. So we consider the case that Team A goes first. So in other words, by going first, we mean it, if it goes first and it can use shared randomness, then you're back sort of in the von Neumann case, right? So then with shared randomness, we each use some strategy, and then we have strong duality, which tells us that it actually doesn't matter that Team A went first. Normally that's a disadvantage, but if they can share randomness, it's not a disadvantage. That's strong duality. In the true multiplayer game, when they have to use private randomness, all they can achieve is this value, the minimum overall little p of the maximum over what the second team can do. And the second team just chooses something deterministic. So the fact that they're restricted to a product strategy is not a restriction at all. They just reply, and they get this payoff over here. And in general, what we have is a weak duality. Team A can ensure this payoff, which happens when it commits first to its product strategy, and then you get some response. Remember, Team A is trying to minimize the number. And that's greater or equal to the value of the game. The value of the game is well defined when you have virtual players, which is greater or equal to what Team B can ensure for itself if it's required to go first. There are two quantities here that we'll talk about, but in this lecture I'll only talk a little bit. This we'll call the defensive gap of Team A. That's what Team A loses by having to go first. This over here, the difference between these two quantities, is what we'll call the defensive gap of Team B. And the sum of those two numbers is what we'll call the duality gap. So the difference between what the value of the game, if Team A must go first and the value of Team B must go first, is the duality gap. And that's what we're interested in here. And the quantity that we study in this paper, well, a few things, but the main thing we study in this paper is the value of this duality gap as a function of M and K. So now we take the worst case game in which there are K players per team, each with M actions available to it. So if you are only going to remember kind of 2 to 3 bits from this talk, is that for all K and M greater than 1, we essentially determine the value of this gap. Okay. Before I tell you kind of the statements of the theorems, let me just point out kind of a little bit of an implication. The implication is that, look at any multiplayer game has Nash equilibrium. Look at any such Nash equilibrium. Okay? It's always the case when there's a duality gap like this. It's always the case that Nash equilibrium is unstable to, if the players of a team could get together and just, there's always some shared strategy that they know once one of the team is playing its Nash equilibrium, that could all, if they would all defect simultaneously, then they would all do that, and they would all know what to do. Okay, this, despite the fact that this is a zero-sum game. Okay, so it's a little bit, maybe not, a little slightly counterintuitive. And maybe just to mention the connection to this sort of sexual evolution, there's been a bunch of literature recently, in case you've been following it, if not. First literature that looked at what happens evolution of a single species against a fixed evolutionary background. It turns out that in that situation, you sort of lose genetic diversity. You tend to a monoculture, sort of a perfectly optimized genotype takes over the whole population when a species is evolving sexually against a fixed environment. Here, if you think of two species kind of co-evolving in response to each other, this kind of provides a possibility that you will not tend to an equilibrium, but you'll enter dynamics that are constant, continually, endlessly kind of evolving. And that's something I'm not going to talk about at all. It's something that Georgios Piliouros and I have studied recently, and I'm further studying with some other people. So maybe that's an advertisement for future work. Here are the statements of the theorems in the paper. The gap when there's K players per team and every player has 2 actions. So 2 is the maximum the gap could be, because in these tensors, I don't think I really said this anywhere, we're assuming all payoffs are between 1 and -1. Okay, so the maximum possible gap you can have ever between any payoff is 2. And what you see here is that already for K equals 2, and already 2 players per team, the actual gap is already 1. Okay, so it's already half of the maximum it could ever possibly be, and in fact it tends toward 2 very quickly with the number of players.
So just to clarify, the gap is defined as the maximum of all possible games?
That's right. I find the worst case game, and I look at the gap of that game. That's right. Worst case game where it's involving K players and M, choices per player, actions per player. Now, this theorem this is equals. We know this number exactly. In other words, I can give you a game that exhibits this, and upper bound that matches it. When there are many choices per player, things get considerably more complicated. But we still know the asymptotics up to a little o1 in the exponent. So it scales like 2 times 1 minus. It has the same form. Look at the right-hand side. It's a little bit easier. The upper bound is kind of identical, except for m. And then there's a little bit of loss in the exponent, but it's almost nailed. Okay. And then something I really won't say anything about here is we also have an understanding of what happens if the players from the 2 teams have to kind of commit to their strategies in some interleaving. Okay, and it's very actually interesting to look at what happens under those conditions. So there exist games with a constant duality gap, but in which adjacent transpositions affect the payoff very little. Okay, so certainly won't be able to say anything about that. In fact, I won't be able to say in this time anything about the proofs of theorems 1 or 2 either. I'll give you only a few words about why there's a big, what gives a game a big duality gap? What feature of a game forces a large duality gap? Here's how you get that. You start with a 2-player game in which both players have to play randomized strategy. That's typical for a 2-player game. So it's almost any game will have that property. And now you kind of lift this to a multiplayer game, roughly as follows. You say, imagine each of the players is, you say if all the players on the team try and do the same thing, then great, then that's what the team does. And if they fail to all say the identical thing, well, they basically lose if the other team manages to all say the same thing. And then if neither team manages to get together, then it's a draw. Okay? So if players don't randomize, they'll lose all the time because the other team will just do something that beats that. But if they do randomize, then they usually fail to agree with each other. Okay, this kind of phenomenon is this you can almost just go home and take and turn into a proof of the m equals 2 case. The m large case is actually harder because this is not actually a sufficient sketch of the idea you require. So there's one fun lemma, since I actually want to do some math here and not just tell you about math. Let me tell you one lemma that you perhaps don't know, which we needed on the way, and it's just a nice combinatorial thing. Here's the thing. We're going to look at sequences, an action by a player is a vector from the alphabet 1 through m of length k, right? Okay, so let's talk about strings of length k from the alphabet 1 through m. For a sufficiently fast growing function h, but only if that's only a function of m. Remember, think of m as fixed, it's just the number of choices per player, and the team size k going to infinity, okay? So here's the lemma. For a sufficiently fast growing function h, and letting g of m be exponential in h, actually 2 to the is about only you need here, but anyway, there is a function epsilon tending to 0 such that the following thing happens. I choose g of m strings in m to the k. Okay, so you should think of this as a constant size set, right? Because m is constant, k is tending to infinity. This is a constant size set. So I pick a sufficiently large constant size set in m to the k. And each string is just chosen uniformly independently. Okay, it's just a random string and they're completely independent of each other. Then with high probability, any product distribution on m to the k, okay, has the property that except for a very small set of strings, except for h of m strings, all of the rest of the strings in your set have probability just about m to the minus k, the same probability they would have had in the uniform distribution. Okay? So you're not able to concentrate much mass on any. You can, if you want, you can concentrate all the mass of the product distribution on a single one of your strings S, right? That's product distribution. You can make one string be very heavy. You can make two strings very heavy. You can make h of m minus 1 strings very heavy. But the h of m string can have probability only like m to the minus k, just what it would be in a uniform distribution.
H doesn't depend on k?
That's correct. That's correct. So only constantly many strings can have a noticeable probability relative to the uniform distribution. Okay, so that's kind of a cool lemma we needed, and you might remember from this talk. Okay, that's it. There's some discussion. I don't know how we are on time for discussion. I already mentioned there's a connection here to replicator dynamics. Replicator dynamics is this sexual evolution process that I mentioned. One thing we don't know is, are there some nice sufficient conditions for gap to tend to 0? Like, so it's not enough that we know that it's not enough to make games be symmetric. We don't know a kind of a natural combinatorial. We think it should be the case that there are a lot of natural games where it's sort of don't lose by having to go first, but we don't know any good characterization. So I think that's a really interesting question. One question that people have asked me when they've heard this, and it's a reasonable thing, is what actually is the gap if I just create a random game? I just make a big table of random payoff. So that's a nice kind of question. Well, maybe a nice question in probability. I don't know. Actually, I haven't devoted thought to it, so I can't guarantee to you it's a nice one, but it might be. Maybe there are interesting distributions. I think it would actually be interesting. Well, these kind of 2 points are kind of 2 points in one. To look at more general kind of classes of games, not just zero-sum games, and sort of, maybe multiplayer games themselves, and lift each player to a team and ask kind of how that affects dynamics. After all, interactions between firms or between biological species are not actually just, a pair interacting. So it'd be very interesting to see kind of what happens. I don't even know to tell you like which questions exactly to ask. It seems like, some. And also, it's also, maybe one could say something interesting about, when the payoffs in teams are not identical, players starting to defect. It might be there's something to do that. I would say that this kind of thing is more my kind of favorite question from this list. But maybe I'll just leave it there.
Let's have the next speaker. We can ask if there is a question for the.
Do you see examples of this gap, duality gap, happening in real-world games?
Well, I think it is a good model for what's happening in the sort of sexual evolution. Of course, that's much more complicated than what this is, and I think these gaps are unavoidable. You took a random game; it's there. So, I can't. Maybe one place it comes up is in sports. There's always the problem in volleyball of who jumps for the ball, who dives for the ball, and there's a certain penalty if they don't coordinate. So.
I mean, in politics, right? Brexit is some duality. Yeah.
We're talking about rational players here.
Can you explain again? Explain the two gaps one can think of. One is what you lose for going first, and the other one is the cost of non-coordination. So how are these two related?
The team that gets to go second has no coordination problem because they have a dictionary lookup of what's the best response. So, it's the penalty for when your order is such that you have to go first. Your penalty for lack of coordination.
So you're comparing full coordination to full independence, but then could you have like a trade-off where you limit communication?
Sure. Yeah, that would be great if we had a communication complexity kind of version of this. That would be cool.
The existence of this duality gap suggests that in evolution, genes that cooperate with each other should end up on the same chromosome and close together so that
So they get
their
selected
crossovers
for
aren't
together.
independent. So is there biological evidence that happens?
Yeah, so this model, this weak selection model that this is so closely related to, assumes it assumes that there's complete mixing, and that we know that's false over shorter time scales, and things do tend to get co-located. But I don't know if biology. I've heard that people say that things tend to get, if they are functionally related, they tend to get co-located. But
Let's take another again.